This wind turbine is based on an ancient mathematical principle so effective that it may be the closest any residential machine has come to perfecting wind capture. Known as the Archimedes Wind Turbine, it runs quieter than a calm conversation, poses almost no threat to wildlife, and in some hybrid systems helps homes reach over 90% annual energy self-sufficiency. Yet most people have never seen one, and few ever will. So why has such a promising design remained so rare? To answer that, we need to explore its ancient origins, modern reinvention, and the economic barriers holding it back. To understand this turbine, we need to go back more than 2,000 years to the world of Archimedes. In the 3rd century, BC, King Hiero II of Syracuse commissioned an enormous ship called the Syracusia, designed to be the largest vessel of its time. But its size created a major problem. The hull leaked constantly, and removing the water by hand required more labor than the ship could reasonably carry. Archimedes responded with a brilliant solution: a spiral blade enclosed within a cylinder that could lift large volumes of water with minimal effort. The same principle soon appeared in Egypt, where it raised Nile water into irrigation channels, turning dry land into productive farmland. Later, the Romans used similar screws to drain groundwater from deep mines. For centuries, the Archimedes screw remained one of the most efficient methods ever devised for moving fluids with simple mechanical force. What began as a practical tool for ships, farms and mines would eventually inspire a completely different kind of machine, one designed not to move water, but to capture the invisible energy flowing through air. That modern transformation began in 2003 when Dutch inventor Marinus Miramet asked a simple but powerful question: instead of using a screw to move a fluid, what would happen if a fluid were used to move the screw? By reversing the logic of the ancient Archimedes screw, he reimagined the concept as a wind rotor. Rather than designing it for open fields with smooth, predictable airflow, Miramet shaped it specifically for the chaotic, shifting wind conditions found around rooftops and built environments. His design turned the screw into a conical spiral, capable of converting unstable air movement into usable rotational energy. The first patents for this new system were filed in 2006. After years of testing, refinement, and field development, manufacturing began in South Korea in 2016. The best-known commercial version became the Liam F1 turbine. What made it especially interesting was not just its unusual appearance, but its promise of solving the biggest weakness of traditional small wind systems: poor performance in real residential conditions. Traditional residential wind turbines are usually built with 3 narrow blades and operate on the principle of lift, much like an airplane wing. As wind passes smoothly across the blade surface, it creates a pressure difference that drives rotation. This system works well only when the airflow is steady fast enough and coming from a fairly consistent direction. That is exactly where the problem begins. In most residential settings, especially on rooftops or in urban neighborhoods, wind rarely behaves that way. It swirls around walls, trees, chimneys, and nearby buildings, constantly changing speed and direction within seconds. Under those conditions, conventional turbines struggle badly. At wind speeds below roughly 9 to 11 miles per hour, many small models generate almost no meaningful electricity. When the wind changes direction, the entire turbine body must rotate to face it using extra mechanical systems and adding more wear over time. In turbulent zones, this repeated reorientation causes vibration noise and inefficiency. It also creates the familiar rhythmic thumping sound that often triggers complaints in residential areas. Worse still, the stress of operating in unstable airflow can shorten the turbine's lifespan without delivering worthwhile energy output. In short, the classic 3-blade design was never truly optimized for the messy, low-altitude wind conditions where most homeowners would actually try to use it. The Archimedes wind turbine solves those problems through geometry rather than brute force. Its rotor is made of 3 curved blades wrapped around each other along a horizontal shaft, forming a 3-dimensional conical spiral. The shape is often compared to the Fibonacci sequence or the shell of a nautilus, where each curve expands in a balanced natural progression. Instead of depending on a thin blade slicing through smooth air, this design works by guiding wind through the spatial volume of the spiral itself. As air enters the front of the turbine, the conical form compresses and accelerates the flow along the curved surfaces. In the process, the wind is redirected by roughly 90 degrees as it passes through the rotor. That redirection allows the turbine to extract kinetic energy more effectively from unstable air. Rather than relying only on lift across a narrow blade profile, it creates a pressure difference through the entire rotating form. This makes the turbine much better suited to the chaotic wind patterns found near rooftops and built structures. What looks unusual at first glance is actually the key to its performance. The spiral shape is not decorative or symbolic. It is the mechanical reason the turbine can remain stable harvest, low-speed wind, and continue working in conditions that would cause a conventional residential turbine to stall, rattle, or fail. The Archimedes turbine offers three major mechanical advantages that make it far more practical for residential use than a standard small wind turbine. The first is automatic yawing. Because the spiral rotor is aerodynamically balanced, it naturally aligns itself with the wind without needing electronic sensors or powered yaw motors. In places where wind direction shifts constantly, that is a major advantage because it reduces mechanical complexity, energy loss, and long-term wear. The second advantage is its tolerance for multidirectional airflow. Even though it is technically a horizontal axis turbine, it can still capture wind entering at significant angles, reportedly up to around 60 degrees from the axis. That means it can continue producing power in the swirling, uneven air commonly found above rooftops, where conventional turbines often stall or perform erratically. The third is its low cut-in speed. The Liam F1 can begin generating useful electricity at about 5.6 miles per hour, while many conventional turbines of similar size require closer to 11 miles per hour before they produce meaningful output. That difference is enormous in real residential environments where average wind speeds are often modest. Together, these three properties explain why the Archimedes design performs so well in places where ordinary small turbines struggle. It is not just a different-looking rotor. It is a machine built specifically for the realities of household wind energy. The strongest argument for the Archimedes turbine is that its design is supported by real-world performance data, not just theory. The manufacturer claims that the Liam F1 can reach about 80% of the theoretical maximum defined by the Betz limit, the physical law that sets the upper boundary for how much wind energy any turbine can capture. Independent researchers have published more conservative estimates, but even those still suggest that the design can outperform many conventional small-scale turbines by a wide margin. Some of the most detailed testing was carried out by Pusan National University in South Korea. There, the turbine was evaluated in environments ranging from calm areas to coastal sites exposed to typhoon conditions. The results showed reliable self-starting behavior at low wind speeds, stable operation in turbulent airflow, and no major structural failure under conditions that would challenge many traditional residential turbines. Its performance becomes especially compelling when combined with solar panels in a hybrid setup. In documented systems, annual household energy self-sufficiency increased from around 61%, with solar alone to more than 92% when the Archimedes turbine was added. Much of that gain came during autumn and winter, when solar output is naturally weaker and wind becomes more valuable. Beyond efficiency, the Archimedes turbine also addresses two of the biggest public objections to residential wind power: noise and wildlife harm. A conventional small turbine can produce around 65 decibels during operation, often with the repetitive thumping sound caused by fast-moving blade tips cutting through the air. The Archimedes design avoids that problem because it has no exposed blade tips in the usual sense. At full operation, reported noise levels are below 45 decibels, closer to light rain and quieter than a normal conversation. Its effect on birds and bats is also very different. Traditional turbines can become a near-invisible blur at high rotational speeds, making them difficult for animals to detect in time. The Archimedes turbine rotates more slowly and remains visually solid, giving wildlife a much clearer obstacle to avoid. Across years of field testing, documented bird strikes on spiral turbines have been described as extremely rare or virtually non-existent. If the Archimedes turbine is quieter, safer, and better suited to residential wind, why has it not become the standard? The biggest reason is economics. A system like the Liam F1 typically costs between $5,000 and $7,000. In an average urban setting with wind speeds around 11 miles per hour, it may generate roughly 1,500 kilowatt-hours of electricity per year. At a common US electricity price of about 15 cents per kilowatt-hour, that equals annual savings of only around $225. At that rate, the payback period can stretch beyond 20 years. In stronger coastal wind zones, the economics improve significantly, and the return period can fall below 10 years. But for most homeowners, comparing options, solar panels still look more attractive because they usually recover their cost much faster, often within 6 to 8 years. That makes the choice easy for anyone focused mainly on financial return. In other words, the Archimedes turbine is not held back because it fails technically. It is held back because a good machine is not always the same thing as a profitable mainstream product. Money is only part of the problem. In many places, installing a residential wind turbine also means facing regulatory and practical barriers. A unit of this type can weigh hundreds of pounds, so mounting it on a roof often requires structural engineering approval to confirm the building can safely handle both the load and long-term vibration. That alone adds cost and delay. Homeowners associations may also block installations because of aesthetic concerns or fears about noise and shadow flicker, even when those concerns are exaggerated. Unlike residential solar, which benefits from clearer legal protections, in some states, small wind systems often remain subject to local discretion. On top of that, there is no mature installer network for this technology in the United States. Many buyers must rely on custom setups or do-it-yourself work, which sharply limits adoption beyond technically confident early users. For anyone seriously considering an Archimedes turbine, the first step is not buying hardware, but measuring the wind. Because wind power rises with the cube of speed, even a small difference in average airflow can dramatically change annual output. A proper wind audit should be conducted at the exact installation height for at least 3 to 6 months. In general, a site should average around 10 to 11 miles per hour before the investment begins to make practical sense. Placement also matters. The turbine must be installed well above the roof line and nearby obstacles to escape the turbulent boundary layer that forms around buildings. Cheap imitation spiral turbines should also be avoided, since many use poor materials and undersized generators that do not reflect the real design's performance. Electrically, the system needs a wind-specific MPPT controller, a dump load, quality battery storage, and proper protection electronics. In most cases, it performs best as part of a hybrid setup paired with solar, not as a standalone source. The Archimedes Wind Turbine proves that an ancient idea can become a remarkably modern energy solution. It is quieter, smarter, and often better suited to residential wind than the machines that replaced older concepts. But high-cost, weak policy support and limited installation pathways have kept it from becoming mainstream despite its real technical promise.